Okay, so this is another in our series of videos to give additional insight into linear algebra that supplements Strang's book. So in this case, we're going to take off from a diagram that is in Strang's book, talking about a matrix A, okay? And here he's relating the different spaces of the matrix A. First of all, on the left-hand side, we have the row space and the null space. Now, if A is an m by n matrix, right? Then each of the rows is in R of n. So the row space of A is in R of n. Okay. Now, when I multiply A by a vector on the right, column vector on the right, this also has to have n entries. Okay. So this is a column vector. Now, the null space will consist of column vectors that multiply by A and give 0. So the dimension, so the column vector is also in Rn. So that means that the null space consists of column vectors that multiply and give 0. So the null space and the row space live in the same Rn. So that's important to realize. It seems that you're switching rows and columns because the null space you think of as column vectors, the row space you think of as row vectors. But that's why it works, because the rows of A multiply by columns when you multiply the matrix A by a column vector. And the number of entries in that column vector must be equal to the number of entries in a row. Okay, so these two live in the same space. Now, similarly, we have the column space of A, which is the range of this mapping. When I apply a matrix A to a vector, then the column space, then we know the result is a linear combination of columns. So that's the range of this mapping that's given by this matrix. And null space of A transpose, you get this if you look at things the other way. If you take transposes, the column space lives in Rm, where m is the number of rows. And if you take the transpose, that's going to be the number of entries in a vector that you multiply. So I'm not going to talk too much about this one, but it's a nice symmetry, but I'm not going to talk about that much in this video. All right, so I'm going to focus on this statement here, that the row space maps to the column space. Okay. Now it's clear that when you take a matrix A applied to vectors in the row space, they must go into the column space. But it's not necessarily true that it's onto the column space. So I want to talk about this. Why is it that the row space maps onto the column space? And in fact, it's also a one-to-one mapping as well. But we'll see that a little bit later. But so I want to, so here, let me just cross this out for a second. It is one-to-one, but we'll see that later. Okay. So what I'm trying to prove is that the matrix A, so the matrix A goes by, so A maps X to AX, right? That's what A does. It maps X times by multiplying, okay? So I want to say that this mapping maps the row space onto the column space as an onto map, Everything in the column space can be obtained as a row space vector times A. Okay, so that's what I want to show. A of the row space of A is equal to the column space of A. Why is this mapping onto? Why is not the A of the row space a subset of the column space? Okay, so we can talk about this in different ways. The first proof is a dimensionality argument. Okay, we've proved before that the dimension of the row space is equal to the dimension of the column space. Okay, so let the dimension of the row space be R, and let B1 through BR be a basis for the row space of A. Okay, so consider these vectors AB1 through ABR. So in other words, I'm taking the basis of the row space and I'm mapping them, and I want to see what happens to them when I map this basis of the row space. Typically, when you want to see what happens to a space, you look at what happens to the basis vectors. So you go from the space to the vectors. And that's a lot easier because you can't operate on an entire space, but you can operate on individual vectors. All right. So I'm going to operate on these basis vectors B1 through BR, and I want to see what happens to these. So in particular, I want to ask, are they linearly independent? That's always a good question to ask about vectors. And in this case, it's going to be the key. All right. So let's see if we can tell whether they're linearly independent. Well, let's find coefficients C1 through CR. such that that gives me a linear combination of these vectors that gives me 0. Now we know that if these are linearly independent, the only solution can be C1 equals dot dot equals CR equals 0. So we're going to start out with this equation, and in order to show that these are linearly independent, we're going to show that in fact C1 through CR must be equal to 0. That's the only possible solution for this equation. All right. Now, so if I take this linear combination of AB1 through ABR through my commutative and associative magic, I can move the C inside, right? We know a constant times a matrix times vector. I can move the constant inside and multiply it directly by the vector. Okay, but then I have A times CB1 plus A times C2B2 plus A times dot 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 plus A times CR BR. I can put those together as a linear combination. Okay, so that's a very important point, that the linear combination of the mapped vectors is the same thing as the mapping of the linear combination. And we've seen things like that before. It's actually called the homomorphism property. Okay, so we've got this linear combination. We've transformed it to this linear combination. Okay, so we can write this vector here as x. All right, this vector is x. Okay, just call this x. Right. So I say ax equals 0. Okay, that's what happens to this vector x, where x is a linear combination of the basis vectors. Aha, but what do we know about basis? The basis vectors are linearly independent. The basis vectors are linearly independent. The only way to do this is if C1 is equal to C2 equals blah, blah, blah equals CR equals 0. That's the only solution. Okay, so the only way to get a linear combination of these vectors is with the trivial solution. That means that these vectors are in fact linearly independent. Okay, so the mapping applied to the basis vectors of the row space are linearly independent. What does that mean? I have R linearly independent vectors, and so the dimension of this space spanned by these vectors is equal to R. Okay, because I've got R linearly independent vectors. Okay, but I just showed in my previous video that if I have two subspaces and one is contained in the other and they have the same dimension, then they are in fact the same. Okay, so I showed that A of row of A has dimension R. I know the column space has dimension R. I know that A times row of A is contained in the column space of A. So in fact, these are the same subspaces. Okay, so you can refer back to my previous video. In fact, that's the reason why I did the previous video, was to set up for this video. All right, so let's say dimension argument, which is very elegant, kind of a counting argument. Let's do a direct proof. Let's do a direct proof that A maps the row space into the column space. In other words, everything in the column space can be obtained as A times a vector in the row space. Okay, so we can do a direct proof as well. So let's see how this works. Now, we also want to phrase this assertion in terms of individual vectors, because if we have vectors, then we can do operations. If we just talk about spaces, it's difficult to do operations. All right, so the column space, what is that? How is that characterized? It's the set of linear combinations of the columns of A. That's definition of column space, right? You take the columns of A and you take linear combinations of those. Okay, so I'm going to say that Cj are the columns of A. So I'm going to say A is equal to C1 up to Cn. I probably should have used A, but I ended up using C. All right, so if Y is in the column space, then Y is a linear combination. These alphas are coefficients, and these C's are the columns of A. Okay, now what do we want to show? We want to show that the mapping from the row space to the column space is onto. So that means that there must be some vector in the row space that maps to this arbitrary vector in the column space. So there must be some vector x that maps to this given vector y, this arbitrary vector y in the column space. All right, now what do we know about x if it's in the row space? Well, if x is in the row space, then it's a linear combination of the basis vectors in the row space. Okay, so I can write these bj's are coefficients. This bj is the basis of the row space. Okay, bj is the basis of the row space. So just keep that in mind. In this notation, cj are the columns of A, also basis of column space of A. Bj is the basis of the row space of A. Okay, all right, now, so what can we get from this? Well, since bj is a basis of the row space, that means that I can write, so this is a linear combination of the rows of A, linear combination of the rows of A. Now I can write that, but I'm considering this as a column vector. So I'm going to take the transpose of the rows of A, and the columns of this R transpose are just the rows of A. All right? So this is a linear combination of the rows of A. This is just another way of writing that. I'm taking a linear combination of these column vectors, and these column vectors are the rows of A. Okay. Now, as I said, we want to show that there exists a vector in the row space such that AX is equal to Y. Okay, so we want to solve this equation. Now I have an expression for X and I have an expression for Y. So let's plug in those expressions. Now we also know that A is equal to C times R. That's the basic decomposition that Strang emphasizes. Okay, so I can write A as CR. This is the same as A, and this is the same as X, and this is the same as Y. Okay, so I'm just plugging in what I found. Okay, so I can rearrange this and put the R and the R transpose together. C times R transpose times beta is equal to C times alpha. Now, what we're trying to do is we're trying to solve for beta, right? Because once we solve for beta, that means we've solved for X. Okay, so that's what we're trying to do. We're trying to find X. If we find the coefficients of X, then we've found X. All right, so let's see. All right, so we can solve for beta if we can solve this for beta given alpha. For any alpha for this alpha is in the column space of A. Well, no, this is for any alpha because these are coefficients. These are coefficients, so given alpha. So these are arbitrary coefficients. All right, now, we know that the matrix R has R rows that are linearly independent. That's the number of linearly independent rows. Now, R times R transpose is going to be R by R. Now, see, R has R rows like this. So this R rows. I don't know how many columns it has. It may have M columns here. And here, if I multiply by R transpose, this is MR times this. So the result is R times R. Okay, so this R transpose is a R by R matrix. Now, it was one of the exercises in Strang says that the rank of a matrix is equal to the rank of that matrix times its transpose. I don't remember exactly which exercise that is, but that is one of the exercises. You can look it up. I think it's in chapter 1.3 or 1.4. Okay, so those that have the same rank, that means the rank of R times R transpose must have the same rank, which is R. So what does that mean? That means the rank of R transpose, is equal to R, which is the number of rows and columns of R. So that means that R transpose is invertible. So we can invert R transpose. Okay, all right. So if we can invert R transpose, then if I put R transpose on the other side, I can get beta equals R transpose, and that's going to be a solution to this equation that I'm looking for. Right? If I can make R transpose beta equal to alpha, then that means that I can find a solution for beta. Now that doesn't necessarily mean that beta is the only solution. It does mean that we do have a solution, but it's not necessarily the only solution. Okay, but since I have a solution, I can find a vector X that maps to the vector Y. So this is an onto map. Okay, question, can we also prove that A is 1-to-1? So that's the next step. If we prove it's 1-to-1, then we're really showing there's a strong correspondence between the row space and the column space mediated by the matrix A. Okay, all right, so how do we prove that something is 1-to-1? We want to show that, so we want to show the following. We can show that if AX is equal to AY, then that implies X equal Y. If I can show this, that means that A is a 1-to-1 mapping. Okay. All right, so let's take two row vectors, X and Y in the row of A, and suppose that they're equal. And then I can use my linearity properties to take the AY to the right-hand side. I can use my associativity to group the X and Y together. Okay, so I have that A times X minus Y is equal to 0. Now, if X is in the row space, it can be written as a linear combination of the row basis vectors and Y also. So I write these out as basis vectors. If I do this, then I get this result. All right. Now, the only way that X minus Y can be 0 is if all of the coefficients are 0. Okay, so all the coefficients of this combination are 0. That means AJ equals BJ. That means X equals to Y. Okay, so the only way to get AX equal to AY is if X equals Y. So from the row space to the column space, A gives a 1-to-1 and onto mapping from the row space to the column space. Now this is quite incredible because A itself may not be invertible. A could be a non-square matrix. It could be highly non-invertible. It could map 1,000 dimensional space down to a 5-dimensional space. That's certainly not invertible, but it does map. It does create what we call a one-to-one correspondence or isomorphism between the row space of A and the column space of and its column space. So that's really quite a, if you think about it, that gives a lot of insight into what matrices do. You can just think of it as kind of a squishing or a distortion of row space into a column space. Okay, so that's the end of that video. Hope you enjoyed it.